Hi, this is the Unit 4 class highlights, and this is just going to be a review for the midterm exam, which covers chapters 1 through 6. All I'm going to do today is go through some problems. I've taken these off of some of my old stats exams, so they won't look exactly like the ones on your sample midterm. They won't look exactly like the ones on your real midterm, but we should be covering all of the topics that you can expect to see on that midterm. Now, this first problem is actually from Chapter 2. It's about a frequency distribution, and we're given a frequency distribution for some TV show ratings. We need to create a relative frequency distribution out of that. So the first thing to do is to find the total frequency. So the total number of households that were asked to rate the TV shows was 5,000. Now, for each one of these, for the relative frequency, we take the frequency for that rating category and divide it by 5,000. So for this first box, we take 375, divide by 5,000, and that gives us 0.075. And notice these are relative frequencies, so I'm leaving them in decimal form. For the next box, we're taking 813 and dividing it by 5,000, which gives us 0.1626. The next one is 1,067 divided by 5,000, and so on. And it says in the problem down here to round to 3 decimal places, and I forgot when I was writing these in, so some of them I carried them out to 4 decimal places. Now, when you get done with this, if you want to check your work, then you would take all the relative frequencies and add them together. And if you've done this correctly, they should add up to 1 or something very close to 1. You can get something just a little bit off due to rounding error, especially if I had rounded these to 3 decimal places like the problem asked me to. But it should be fairly close. It should be 0.99 or 1.01, something like that. It shouldn't be very far away from 1. Next question is, what type of data is the rating variable? Is it qualitative or quantitative? And remember that when we have just categorical data like this, in other words, if it's put into words, then it's going to be qualitative data. Qualitative data, it would have to be either the nominal or the ordinal level of measurement. And since this one we can put it in order from poor up to excellent, that makes it the ordinal level of measurement. Next problem. Here we have 2 frequency distributions, ticket amounts for female drivers and ticket amounts for male drivers. And the first question is, what are the class widths for these frequency distributions? And they both have the same one. Now remember, to find a class width, you have to look at the difference between the lower class limit in one class compared to the lower class limit in the next class. So if we look at the first 2 classes, the first one starts at $25, the next one starts at $55. To get from 25 to 55, that's a difference of 30. So that means the class widths are 30. Next question is, approximately what percentage of male drivers in the study paid less than $85? Well, if we look at those first 2 categories, those are both less than 85, and we've got approximately 5% for one and approximately 15% for the other. So if we take the 5% plus the 15%, then that's going to give us approximately 20% of the male drivers that paid less than $85 for their ticket. For the females, again, it's those first 2 classes. Those are both under 85. So in that first one, we've got what looks like about a 43, and for that second class from 55 to 84, that might be a 36 or a 37. So if we take the 43, and I just said this was 36% for the second class, if we take those 2 and add them together, we're going to get 79%. So this would be approximately 80%. The last question here is there anything misleading about the way these graphs are presented? And if so, what should be changed in order to correct this? Well, since we've got the 2 graphs that are comparing ticket amounts for females and males, look at the differences between them. And specifically on these 2, look at the differences in what's at the top of that vertical scale. Females, it's 50%. For males, it's 70%. So that is a little bit misleading because it makes it look like the frequency for the males in that middle class, the highest frequency, is about the same as the frequency for the females in their highest class, but that's really not the case. So what we could change in order to correct this is to make them both with the same scale. For example, we could change the graph for the female drivers' ticket amounts so that it went all the way up to 70%, and that would make them the same scale. Next question. This is from partly from chapter 3 and partly from chapter 6. So we have the average ticket price for a Denver Broncos football game was $93.20 last year. With the cost of parking, food, drinks, and souvenirs, the mean cost for a family of 4 to attend a game was $503.66. The standard deviation was $68. Assume that the cost distribution is approximately bell-shaped and symmetric. In other words, it's a normal distribution approximately. So if we want to find the z-score for a family that spent $364, and then we're going to look at that z-score to decide whether this should be considered an outlier or not. So first we write down the little formula for the z-score. Remember, that's x minus the mean divided by the standard deviation. And the number that we're interested in this case the 364, that's going to be the x. The mu is the mean that was given us in the problem, and the sigma is the standard deviation given us in the problem. So here's what the form when we put in the correct numbers in the correct places. Notice that the 364 is smaller than the mean, so when we calculate this, we're going to get a negative z-score. And that's fine. Z-scores can be either negative or positive. Next question, should this be considered an outlier? Well, technically, according to this book, if the z-score is less than -2 or greater than +2, we do have an outlier. This one would barely be in that range. Next problem, we're finding the z-score for another family that spent $725. Now this family was above the mean, so when we plug our numbers into the formula, this time we'll get a positive z-score. When we calculate that out, it's going to be 3.26. So this one is definitely an outlier because this one is more than 3 standard deviations away from the mean, so we would for sure consider that one an outlier. Now the next two problems actually come from chapter 6, but we'll go ahead and talk about them here. First, what's the probability that a randomly selected family spends between 503.66 and 639.66? If we're going to do this using the table, the z-scores table, then we need z-scores for both of these numbers. So here I'm figuring out the z-score, and notice since our first number is actually the same as the mean, we get 0 for the z-score. For the second one, and again we're plugging $639.66 into our formula for the x. And if we calculate this, we're going to get a positive 2.00. Now here, remember when we're doing probabilities with the normal distribution, with z-scores, then I really would recommend that you draw the picture. Here's the picture of our distribution. We've got our mean right there in the middle, and our two values are 503.66 and 639.66. So we're going to draw both of those on the graph. And we want the probability that the value is between those two, so we're going to shade in between the two. So what we have to do for this, if we're going to use the table, is that we have to find the probabilities for each of our two z-scores from the table and then subtract our probabilities. So if we look up z equals 0 in our z-scores table, we'll get 0.5. If we look up 2 in our z-scores table, we get 0.9773. To find our probability, we're just going to subtract those two, and that's going to give us 0.4773. Now the next problem is, what's the probability that a randomly selected family spends less than $435.66? Same idea again. If you're using the z-scores table, then you have to find the z-score for the 435.66 first. This comes out to be negative 1.00. Here's our distribution again. I'm putting the mean right there in the middle. Notice if you're doing the z-scores, you can also put 0 in the middle, since that's the mean for your z-scores. And our x value, our 435.66, is to the left of the 503.66. And since we're looking at a less than, the probability that the family spends less than that, then we're shading to the left. That means since we found our z-score already, we're trying to find the probability that z is less than negative 1. If we look up negative 1.00 in our z-scores table, we're going to get 0.1587. And since the z-scores table does less than, we don't have to do anything else with that. That's our final answer. Now here I'm going back to do the normal CDF for the previous problem. I forgot to do it. So remember, on your calculator, you don't necessarily have to convert to z-scores. So on the calculator, you'd put in the two values, the 503.66 and the 639.66, and then put in your mean and your standard deviation. And in part D here, we're going to put in a big negative value for our lower bound because our graph is going all the way out to the left, and then our value of 435.66, then our mean of 503.66, our standard deviation of 68. And we should get something very close to the 0.1587 that we got from the table. All right, next problem. We're looking at a whole set of data with several variables, 6 variables actually, and we're looking for, well, what we call the level of measurement for each one. Now, this problem came from a class that uses a slightly different book and has a little bit different terminology. So in that class we called it the scale of measurement, but it's really the same thing. So we're trying to find the level of measurement. Now the first variable, the items variable, that would have a natural starting point of 0, and ratios would make sense, so that's at the ratio level. Sales is the same thing. Notice these are both numerical. Gender would be nominal because it's just categorical and order doesn't make any sense. Same for marital status. Now for the age category, this is categorical, but we could put this in order from youngest to oldest. So that would be the ordinal level. And the account start date, since these are dates, for time, there's no natural zero starting point. So this would be at the interval level. Now here's a frequency distribution. And first we're trying to find the mean age of the customers in the survey, just given the information in the frequency distribution. So what we need to do is find the class midpoint for each class. And then if you remember, we're going to multiply the frequency for that class times the class midpoint. So let's go over here and find our class midpoints. To do that, we take the upper and the lower limits and add them together and divide by 2. We're just averaging them. So for the first class, it would be 27. For the second class, we're taking the 35 plus the 49 divided by 2, which is going to give us 42. For the third class, we end up with 57. And for the last class, we have 65 plus 79 divided by 2. Which gives us 72. So here are all of our class midpoints. And then I'm adding another column to this where we're going to have the frequency times the class midpoint for each class. So we're going to multiply the frequency by the midpoint. So for our first class, we're multiplying 29 times 27. That gives us 783. Next class, 44 times 42 gives us 1,848. Third class, 21 times 57 is 1197, and last of all, 6 times 72 for the last class gives us 432. Now we're going to add all these up. So if we add all those up, we get 4,260. Then we're going to divide by the total of the frequencies. So we're adding that frequency column. If we add that, we get 100. So for our final answer, for our mean, we take 4,260, divide by 100, and that's going to give us 42.6. Now the last question in this problem is just what is the class width of the frequency distribution? Again, all we have to do is look at the difference between two consecutive lower class limits. So for example, from the first class to the second class, if we're looking at the lower class limits for each one, we've got 20 and 35. So from 20 to 35 is 15, and that means our class width is 15. Internet users were asked if they wanted to live to be 100. There were 3,042 responses of yes and 2,184 responses of no. If we're trying to find what percentage of responses were yes, then we have to have the total that took the survey. So we have to add the 3,042 and the 2,184. That gives us 5,226. So to get the percentage of yeses, we take the 3,042 that did answer yes and divide by our total. And if we divide that in decimal form, we get approximately 0.582. If we're going to write that as a percentage, we get 58.2%. And remember, that's because we move our decimal place 2 places to the right. Now for part B on this one, we're just using the same answer that we already got. The probability of randomly selecting someone who does want to live to be 100, if we use the information from this survey, we would say that that would be 58.2%. But if you look at the last question here, what term is used for this type of sampling method, and is this sampling method suitable? Well, if you look at what they did, this was an America Online poll over the internet, so we would assume that it's a voluntary response sample. And that means that the results are going to be biased, that the people who answered the question were ones that had some kind of strong opinion about it, and that means that it's not suitable. Okay, here's some different questions from Chapter 3. We have a set of data of weights of steaks, and these are supposed to be 20-ounce porterhouse steaks, as it's listed on the menu. The weights are supposed to be 21 ounces because the steaks supposedly lose an ounce when they're cooked. So first we want to find the mean weight of all these steaks. So if we add all these numbers up, we get 386, and then we have to divide by the total number of values that we have, which there are 20 in this list. So if we divide 386 by 20, we get 19.3. Next question is to find the median weight, and to do that we need to put our weights in order from smallest to greatest. I didn't give myself a lot of room up there, so I'm doing this down here at the bottom. And here I'm listing out all of the weights in order, starting with 17, which was the lightest weight, and the heaviest of the steaks was 21 ounces. So there's our whole list. Now to find the median, we know we have 20 values. That's an even number. That tells us that we have to take the 2 middle values and average them. So we have to find the 2 values in the middle of that sorted list and do an average. Well, the 2 values in the middle would be the ones in the 10th position and the 11th position, which turn out to be 19 and 20. So to average those, we add them together and divide by 2, and that's going to give us 19.5 for our median. Now these next 2 questions were on this test that I had given, but we're not going to do either the standard deviation or the variance. So I'm crossing those out. But just based on the results from the mean and the median, do you think that these weigh enough? They're supposed to weigh 21 ounces. Both the mean and the median came out to be under 20 ounces, so probably our answer would be no. These are not very close to the 21 ounces that they're supposed to be. Now let's also find the mode of the weights. And if you look at our list that we had sorted at the bottom, 20 came up 8 times. That was the most of any of the values. So that would be our mode. And now if the standard deviation of the weights is 1.1 ounces, what are the minimum and maximum usual values? If you remember in the book, to get the minimum usual value, you take the mean and subtract 2 times the standard deviation. To get the maximum, you take the mean and add 2 times the standard deviation. So for our maximum, we take our 19.3 and add 2 times 1.1, which would give us 21.5. For our minimum, we take the 19.3 minus 2 times 1.1. That gives us 17.1. So the 17.1 is our minimum usual value. The 21.5 is our maximum usual value. Now finally, what's the level of measurement of the stake weights? This would be ratio, because again there's a natural zero starting point. If one stake weighed, say, 10 ounces and another stake weighed 20 ounces, then it would have meaning to divide the 20 by the 10 and get 2. That would mean that the heavier stake weighed twice as much as the lighter stake. So this is the ratio level of measurement.